Well, welcome to this afternoon series of talks. Now our next speaker is Pedro Frejlich from Universidad Federal do Rio Grande do Sul.
Hello, hello. Can you guys hear me? Okay. So let me start by thanking for the invitation to come speak here. I'm always very pleased to come to Rio, especially like not grading retakes from linear algebra. That feels fantastic. So I should give some disclaimers. First disclaimer is that this is joint work with Yonut, but I hope he agrees. We haven't quite made our minds about that. And so the second disclaimer is that so part of this work was also inspired by work of Davi Martinez Torres and his student on constructing Poisson structures with finitely many leaves. And let's see. Let me remind myself of what the presentation was. Right. Oh, sorry. Smoker, I should. Okay, so also another disclaimer I should make is that I think my main goal in this talk is to introduce some language. So this could be seen as like a linguistic talk more than anything. I want to introduce like a language and perhaps like some small philosophical remarks that unify a lot of like scattered results that will make like some a coherent narrative perhaps a little bit more difficult to achieve, but I think that might be regarded as a plus or as a minus depending on how we view things. And also, like, we live post-Wittgenstein. I'm very much into this philosophy, so yeah, language is important. So let's start with some motivation. Okay, so this talk is going to be about Dirac structures. I wasn't here last week, but I heard that Henrique gave like a very good survey on this issue, and like also being aware of which talks would come. So yeah, let's just go straight to the meat. So the general ambient where we're going to do, like where things are going to happen is the standard Courant algebroid. So I guess that by now, after this morning's talk, we're very much aware. So there's this inner product, and well, both T and T star are completely symmetric from this linear algebraic point of view. But the symmetry that T and T star enjoy in this linear algebraic point of view, it's broken when you plug in the integrability, right? There's this Dorfman bracket, which is written here. And, well, T star, well, the bracket on T star vanishes altogether, and on Tm, it's really, I think that I have to, like, point to my T-shirt to, well, it restricts to the usually bracket on Tm. So this asymmetry of the Courant bracket, well, perhaps the clearest instance of it is in these two examples. So if you have two close-to forms, their sum is a close-to form. Oh, yeah, we're all aware that we regard these as like graphs inside the Courant bracket. However, if you just switch the roles of T and T star, and you have two Poisson bivectors, pi L and pi R, and I want to keep this chirality, there's left and right, their sum is no longer automatically a Poisson structure. It's only a Poisson structure if they commute. So this introduces like a nonlinear PDE, which is kind of, yeah, it's ugly. Okay, so products. So the goal of the talk, as I said, was to introduce, well, half of the story had been introduced before, and I'll remind you of how it went. But the goal is to describe tangential and cotangential products, so which I'll denote tangential by star and cotangential by this circled star, between two Dirac structures, L and R. So they'll always occupy the obvious places in my notation, in such a way that the star product will, or the tangential product, will generalize the sum of two forms, while the circled star, or cotangential product, will generalize the sum of bivectors. Okay, and this is the main gadget of the talk, so to introduce this language and to point out how very simple observations about these two structures, or these two operations, appear like pretty much everywhere in Poisson and Dirac geometry. Okay, and, oh, sorry. And perhaps like to illustrate, this is, okay. Just to illustrate like how I view myself in this talk, let me show you guys one very small video. Can I do this?
Oh, hello. Have you tried Jose today?
Oh, what is Jose?
It's a new word.
Oh, what a wonderful idea. How would I use it?
Okay, it's kind of like if something's really lame, you know? Say I don't like your shirt. I'd be like, you bought that shirt? Jose.
Yeah, it's pretty much that. Okay, so, okay, well, I was promising like an operation between Dirac structures, but as a matter of fact, and this is another of the very small philosophical bits of this talk, is that Dirac structures, they're very robust in their pointwise linear algebra, and the involutivity condition is also quite robust, but the transversality issues are kind of a nuisance. So we kind of like want to keep these conditions apart. So useful language in order to not get bogged down with minor details which are not really relevant, is to talk about linear families. So subspace of t plus t star, which meets every fiber in vector subspace. Very simple, without any condition. It's smooth if this linear family E is a smooth subbundle. It's isotropic if it's included in its perpendicular with respect to the bilinear form. It's Lagrangian if it equals it. And it's involutive if, whenever you have two sections taking values in this linear family, its bracket also does. So let's introduce this notation of Lagrangian of Tm as like the set of Lagrangian families without smoothness, okay? So, wait. Okay, so this tangential product, perhaps let me go back a little bit. This tangential product, I think I first saw it in Marco's thesis, but maybe it was I can't really recall the thesis from the paper. And it also appeared in a paper, Pure Spinors on Lie groups, by Eckhard, Henrique, and Anton. And let me remind briefly what it was about. So it's an operation that takes two Lagrangian families and gives a third one, E prime, and gives E star E prime. Explicitly, it's given by U plus xi prime, where U plus xi is in E, and U plus xi prime is in E prime. Now, this thing might seem it's not perhaps obvious at first why this should be a Lagrangian family, why it should have the right rank. But you should remind yourself that every Lagrangian family can be pointwise written as the gauge transform of its projection to Tm, right? So this operation, if you have another one, I'll decorate with primes the other one, and let's call this one whatever. Then star will be just evaluated at some point. It's just going to be, you sum the forms and you intersect the images. Now, of course, this this expression, well, this thing is automatically defined once you have E, but this omega is only defined on E, or on the projection, I'm sorry. But, and then it's patent that the star is defined, is well defined independently of the forms that you chose. Okay, and this deserves the name of product because of the obvious things like, oh, sorry. It's associative, it is commutative, Tm acts as identity, this should not be here, and T star of M acts as 0. And, well, it's compatible with rescaling, and by rescaling here I mean if E is a certain family, Te is going to be U plus T psi, where U plus psi was in your original E. And it's also compatible with pulling back by an arbitrary smooth map. It's an operation that I think you guys saw when Henrique spoke about it. So this thing has a very nice interpretation geometrically. So if you have two Dirac structures and their star product is a Dirac structure, then the presymplectic leaves of this product is no more than taking connected components of the intersection of the leaves of each one. And the presymplectic form is push the presymplectic forms from either side and sum them. So, but even better, the star product has this very simple interpretation in terms of the diagonal map. So if you put on this copy L and on this copy R, you pull back by the diagonal map, and this is no more than L star. So, okay, this is the literature where it appeared earlier. Now, this description, this very geometric description, kind of ensures that whenever the star product of two Dirac structures has, well, it's smooth, then it's automatically Dirac. That's pretty much the part that connects to, you should think of this as like the analog of sum of two closed forms being automatically closed. So this is just a simple lemma, like, so we are here, we need cleanness, sort of yeah, this is the cleanness that ensures that the leaves are smooth manifolds. And, well, let's introduce also this language of being tangentially transverse when their anchors sum to the whole tangent space. When that happens, this star product has a nice description in terms of, Henrique, did you talk about spinners in the no? Okay, well, so every smooth Lagrangian subbundle, it defines a line subbundle of T star of M, but in all degrees, and L is the kernel of this guy in the sense that an element U plus Xi belongs to L exactly when, for a local representative here, the action U plus Xi, which is contract and wedge, this is 0. Okay, and then the spinner that defines the star product is no more than wedging the two spinners. And this is the automatic involativity that I was talking about. If L and R are Dirac structures and the star product happens to be smooth, then it's automatically Dirac. Now, this is very nice, and just one instance where I think, well, there was this old paper, but really relevant in the development of the courant theory, Manning triples for Lie by algebroids from '97, where they describe like this, well, where they show kind of by force that this bivector pi2 that I will define here was Poisson, and in this language it's just complete triviality. So you just assume that you have two Poisson structures which are transverse in the sense of their graphs, meaning that there is a not necessarily close to form that whose inverse is their difference. Then you construct this kind of recursion operators, lambda I. Then this condition says that every psi is the difference of these. And, well, these two compositions agree, and they define a third bivector pi2. So the graph of pi2 is nothing more than star of the difference of these two. So it's automatically Poisson, and there's nothing to do. OK. Right. Now we go for the actual new language to be introduced, which is cotangent products and concurrence. OK, so the cotangential product, as the tangential product, is an operation well-defined on Lagrangian families. And you would expect, you just switch the roles of T and T star. So U plus U prime plus Xi lives in this cotangent product if U plus Xi is in E and U prime plus Xi is in E prime. Again, the same story applies here. Like every pointwise, every Lagrangian family can also be written as the gauge transform by a bivector of the projection to T star. I mean, you can guess by now that from the point of view of linear algebra, we just really switch one and the other, and then the circled star product will be summing the corresponding bivectors and intersecting, the corresponding projections. And again, the fact that pi and pi prime are defined, well-defined, and independent of choices on these guys says that it's also, the circled star doesn't depend on anyone. OK, and again, this deserves the name of product because it's associative, it's commutative, and now, again, roles of T and T star switch. T star acts as identity, but T acts as 0. And it's compatible with rescaling, but now you have to switch from pulling back to pushing forward. Right? That's the price we pay. Now, we had like this very big lemma after the definition of tangential product, and it got very thin at the level of cotangential product. So pretty much all we can say is that all that remains is the linear algebraic statement. So, and here, here comes our definition. So two Dirac structures, L and R, are said to concur weakly if the cotangential product is involutive. Here, I'm not requiring that it be smooth. It's just that it's involutive as a Lagrangian family. And they concur if they concur weakly and it's smooth. So a very simple thing that will play a role later in this talk is that two guys which concur weakly, you can switch signs and they also concur weakly. So perhaps like the main example after bivectors is that of foliation. So if you have two foliations, FL and FR, then the graph of the sum is the cotangential product of the graphs of these foliations. So you see that it's kind of the reason why I wanted to use another word which we're not commuting or commutativity, but concurrence, because each side contributes to a larger thing. So actually, Yunus said that he doesn't like the word, but I have here like I'm making my case about why concurrence, right? So he said that concurrence was intersection, and I think that there is like, so Shakespeare would disagree, so you have to pick sides at some point. So this is pretty much like so to run together and meet, to combine and conjoin or contribute towards a common object or effect, which is pretty much like what I would like to see in this, from this point of view. Okay, so there was a previous notion of Dirac pairs that Henrique told me like over a beer a couple of days ago that was already in in the book of Dorfman that, well, I happened to take a look at like 2 days ago, and indeed it was there. Only that torsion, the torsion condition was not present. That was the only difference, but the whole notion was present in 93. So, and I was under the impression that this notion of Dirac pairs was what would play the role of commutativity in Dirac geometry. And I got out of this idea, and another byproduct of what I would like to convince you of is that the Nine-house condition has been overplayed. Like, it plays a role, but sometimes as like a consequence more than like the main object. So let's just compare. So a Lagrangian can also be regarded as a relation between T and T star. And, well, we can switch the roles of T star and T, and I'll denote it by L bar. So relations, you can compose if you switch sides of either side. And you see that it's really, really close to the definition that we had, say, in, here, right? It's quite close. Here, let me just go back. Yeah, so two vectors, u and u prime, belong to this composite when there exists psi such that u plus psi and u prime plus psi lie in R. And well, okay, so you see that it's kind of like a projection from that notion. And the tangential version of it is when you switch the first relation. So pairs of psi and psi prime such that there exists in U, such that U plus psi and U plus psi prime lie in R. So you can define this torsion. This is supposed to be Y for Yvette, defined in this paper, which, well, it wasn't really written like that in the paper, but it's just like this observation that the notions of dual of the composites, which would sit here in her definition, actually just, well, they can be expressed in this way. And the torsion is like a complicated beast. It takes like a bunch of guys, and you see that they are not like even very independent, and you cook up like some monstrous expression, and when this guy vanishes, then you call the pair a Dirac pair. Now, okay, this is like it's not very difficult to prove, but it wouldn't be particularly illuminating, so just like, yeah, take this more as a survey. Two Dirac structures which concur weakly, they form a Dirac pair. So the notion of concurrence, even in the weak form, implies already that of Dirac pairs. But not the other way around, and that's kind of like why it's a Nuber condition. So take the simplest example of two things which you would not want to call commuting. ddx and dy plus x dz. These two vector fields do not commute. If you go back to the torsion defined by Yvette, each term in this expression vanishes identically for this example, but of course the sum of these two vector fields does not form a Dirac structure. So that's kind of like part of the narrative. Like concurrence is a better candidate to be analog of commutativity for Dirac structures, and Dirac pairs is more of a recursive notion that is implied somehow. Okay, so now the idea is to use OZ in many sentences, right? Like spelling bee, use it in a sentence. So yeah, okay, this is perhaps like historically in the work with Ionut, it was the first instance when this cotangential product appeared and showed that it was really useful. So if you have a surjective submersion with connected fibers, and you have a Dirac structure on the total space, you also have another Dirac structure for free coming from the fibers, right? This is V is the vertical bundle, and graph of V means V plus V annihilator. So these two guys concur exactly when there exists a Dirac structure on the base M for which the projection is forward. It's a forward submersion. In which case, what is the cotangential product? It's no more than the pullback of the Dirac structure that you have on the base. Right. So this will play a role in the other sentences that we're going to write. I'm doing well. Okay, so I think this next example shows a lot, like in a very clear fashion, the role that cotangential products play in splittings and normal forms. So Luca mentioned to us the normal form, the pointwise local normal form described by Blumen, and this is like a complete proof based on just nothing. So if you have a Dirac structure on a manifold and it meets a close to form in a smooth subbundle, then you can gauge it back and you get a foliation. Call it V. So suppose now that this foliation is simple. So it's defined by a submersion with connected fibers. Then there is a Poisson structure on N, the base, for which L is just the gauge transform of the pullback of that Poisson structure. So, and just as a very brief comment, and this is like how all of this language is pretty much trivial, you can regard this as just you subtract from L omega, and then you add it with parentheses. We're just like summing and subtracting, a standard trick that I teach my Calculus 1 students. And this is the proof. By hypothesis, if you just, by definition of V, the cotangential product of gauging back the whole L with the foliation is just itself. So Lieberman's theorem that I just showed you in the previous slide says that this guy pushes forward. And then it meets Tn downstairs at 0 by definition again of who V is. So that's it. So how does this recover Blumen? Well, Blumen was a local result around a point. So remember that gauge transforming by a closed to form preserves the rank of the projection to T, but not to T star. So you can just, at that point, find an exact form, the alpha, for which this projection is maximal. If it's maximal at that point, it's maximal around it. And then the conditions of this lemma are met because around it, you can also assume that the submersion is simple. So that's it. Okay. Now, things get kind of, well, this is one thing that I wanted to get rid of more or less, but I couldn't actually. Like, there's some results that are still, there's some transversality required, but this is work in progress. I'll get back to you guys. So take two Lagrangian subbundles, L and R. So the following three things are equivalent. They are transverse, so they sum to everything, or they are tangentially transverse, meaning that they sum to T, and their difference, their tangential difference is a bivector, or they're cotangentially transverse, and their cotangential difference is a two-form. Now, this was also present in these two papers, and, well, actually 1 and 2, but 3, as you guys know by now, it's just reversing roles. We are in the linear algebra side here. But this is nice because, so cotangential products not having this description as being like related to maps as like the diagonal described tangential products. This is a useful thing to have like a very concrete integrability condition. So when is the cotangential product of two transverse guys Dirac? Well, it's when a certain certain two form that appears is closed. And that's a very familiar condition, and we like familiar things, right? So, okay, I'm doing very good. Okay, so an example of how this thing appears in the literature is when it comes to couplings. So these products or this language is useful even when the involved condition is not satisfied. So perhaps the most classical example is that of couplings. I should have quoted here like a bunch of people more, but this is the paper closest to the setup, so see references therein. You just have a surjective submersion sigma to m, and you call it coupling when it's transverse to the foliation. And then we know already, because the foliation and minus the foliation are the same thing, you know that the tangential product is a bivector, and the cotangential product is a two-form. Now, tangential of two Dirac guys is Dirac, so this guy is automatically Poisson. Now, the cotangential is not. This is just a two-form in general. And, this will play a role in the next bit, which is, out of these two guys, you can construct also a Nersman connection, which is just projecting the part which is orthogonal, that L meets the V perp. And then you can recover the whole Dirac structure out of the two bits, of the vertical bit and the horizontal bit, as L is the sum of the gauge transform of the Nersman connection by omega and of its annihilator by pi. Okay, so let's try to, here, in the case of when R, the right-hand side Dirac structure Lagrangian is the graph of a foliation, there is an interpretation which I find very useful coming from this paper from Calvo, Falsetto, and Zambon, which is the following very, very simple observation, so simple that it has a proof here. If you have a Lagrangian family and an isotropic family, you can construct a new isotropic family, which is take the part in L, which is orthogonal to E, and sum E. This is a Lagrangian family. Proof, just take annihilators and you see that it's just that. Okay, so the interpretation here is that this new Lagrangian family is the closest Lagrangian family to L among those which contain E. Okay, this is a useful thing to keep in mind and like when trying to formulate like things that you wonder. Okay, so let's try to connect this, and this is the part that connects to the work of Davi and his student, Lilian Brambilla. So if you have a submersion and the Dirac structure in the total space, you cook up the vertical one, so the cotangential product with the foliation, and the horizontal one, so the cotangential product with the foliation. So with this interpretation is like the closest one to L that contains the annihilator of V, and the horizontal one is the closest to L which contains V. And let's call L weakly fibered if they're both smooth, and fibered if they're Dirac. Okay, then you can start wondering about like how much, when can you expect to reconstruct the whole Dirac structure on the total space out of horizontal and vertical bits? And just a very simple thing is that, and this already points towards like this recursion that when you have, let me first read the lemma. If you have two guys which come from a certain L, then the tangential product is already the vertical and the cotangential is already the horizontal. So in particular, if L were fibered, then the two bits that you want to have as candidates for horizontal and vertical bits of a Dirac structure, they have to concur in that language. So use it in a sentence once more. Okay. Now, about, and again, I have to apologize for the lack of like narrative direction, but things, and this little arrow here says that like things bifurcate in many directions, and you kind of have to like pick one side to tell a story while making some references about what would have happened if you went the other way. So for instance, let's assume that that you have splitting. So the vertical part is, which I'm not even assuming here is smooth, so well, see that the vertical bit that is always well defined as a Lagrangian family, it's smooth. Criterion for it to be smooth is that it admits a splitting like this. Same thing for the horizontal one. And then you can construct the candidate Lagrangian families that would have been induced by either side. And they're kind of canonical in this once you are given a splitting. So, yeah, so I will denote this backwards because the tangential is like backwards and the cotangential is forward, right? So that explains the direction of the arrows. And there was this notion that I learned from Vorobiev and Vallejo, a paper that was already cited, I think, on Tuesday, of almost coupling. So a Dirac structure on the total space of submersion. And let me just point out here for a second that being a submersion does not really play a role, right? You could have like just a foliation, but let's be just concrete. So it's almost coupling if there's an Ehresmann connection for which the vertical splitting is just the intersection with the only possible thing. You want to keep it isotropic. And the horizontal splitting is also the obvious thing. Now, in this almost coupling condition, so if both guys are induced from an Ehresmann connection in this fashion, then the whole Dirac structure is recovered as D plus C, and the two candidates that we had, they just coincide. So this is like, yeah, it still retains a lot of the flavor from couplings, but it's more general. For instance, in couplings, you could not have like fibers which are two forms and base which is Poisson. And with this language, you can. And well, right. And our story will generalize this in this very simple-minded way. So as I'm saying here, like we're at this crossroads that we have to pick a side, either go vertical or go horizontal. Let's go horizontal just because, yeah, flip the coin. So just to wave around some things that I don't really want you guys to read, you can describe very easily. So the forward is the one, as we constructed for this to hold, it's the one that induces the horizontal bit that you started from. Now, the vertical one, there are conditions. You need something to happen. To be smooth, well, you can ensure if something else happens, and if it's smooth, you can ensure that it's Dirac. If something else, never mind what the conditions really are. Also, I should point out that, well, there are counterexamples. For instance, you can have L can be smooth without this guy being smooth, and any possible statement that you could make here, there is like a counterexample. So, but in order to have like this reconstruction, let's call L horizontally slanted. If there is this, so if the horizontal splitting can be chosen so that this thing holds, okay? And well, that is the condition that we need in order to recover the original Lagrangian family. We don't need smoothness at all here. To recover the forward candidate. And well, one example of horizontally slanted, perhaps like the one that got me to think about this, was toric Poisson structures. So they are always horizontally slanted, but they are not vertically slanted. So it really shows that like you really should abandon some conditions along the way because, well, that's how life is. So in particular, if you remember from what happens with the almost coupling, both candidates coincide, so this is already like a very simple instance when you know that this is not almost coupling. So it's really more general and shows up in nature, as someone said recently, and I like the expression. Now, this is also, so since we picked the horizontal side to go, let's take this. So this is this small theorem that perhaps is too complicated to read. So if you take a leaf, suppose that the horizontally slanted guy pushes forward to a Dirac structure on the base. Then this pretty much like is a reconstruction of what I called at some point submersions by Lie algebroids along the leaves. So you can think that, so bundles of, so over every leaf of the base, you have like a submersion which has Dirac transversal fibers. And if you put in like some completeness, well, I'm putting this condition here of fibers being compact, but you can replace this by some principality if there's a group acting, and which is the case for toric. Then the restriction, so pick a leaf downstairs, the pre-image of the leaf has the structure of having, well, it's also submersion, forward submersion with the Dirac transversal fibers. And each leaf of the thing upstairs fibers surjectively over the leaf downstairs. And if the Dirac transversals from this item happen to be Poisson, then they really couple over every leaf. So you can think that like it's the coupling example, but made leaf-wise in such a way that the whole thing makes sense. Okay, and here I think that we're going to lose track of like the coherence of the narrative by a lot. But, okay, so, but I need this part also to discuss hierarchies, which I hope we'll get there. So, there's this notion of a Poisson manifold being calibrated, which is that there is an ambient close to form that induces the symplectic structure on the leaves. So this thing implies that the Poisson structure is regular. So it really defines the foliation, and the Poisson structure itself is just a tangential product between the foliation and this ambient 2 form. And well, I found these things interesting because of like some results of the V that say that if you have a compact corank 1 calibrated Poisson manifold, then there is a Poisson transversal of dimension 3 that knows everything about the foliation, which is kind of very cool. So this language gives like a way of generalizing this condition to what I'm calling sub-calibration. So it's just a closed-to form such that when you cook up an endomorphism of the tangent bundle, it's a projection. Okay, so this no longer implies the regularity of the bivector. That's one of the nice things about it. But it still splits the space as you would like. And, well, this guy is always orthogonal for both structures, and it induces splittings both of the form of the bivector, and all that's good in the world happens. Like the image part, they're just inverse to one another, and on the bad part, they just kill one another. So these two guys are pretty much non-regular, but they're non-regular in a way that they don't cause you any trouble. So, and another consequence of this is that you have 3 splittings of the Courant bracket, as pi and minus omega, as pi and k, and as I and omega. So given 3 transverse guys, we can cook up like a bunch of forms, a bunch of bivectors, and as we also know, we can like change signs and get some things which are not even one and the other. Oh, wait. I think the slide is in the wrong place, or I'm just trying to say why. Why I thought these were also interesting things to look at. Because, well, there's this strange thing of Poisson homology that I don't understand at all. Like, there's some statements that you make, and it shows up at times. But what it computes is like a huge mystery. Like, H0 makes sense, but the others, I don't know. So just to say that like sub-calibrations, they're automatically cycles in Poisson homology, and the proof is just absolute triviality. Like the composite, because of those relations here, it's just like the simplest possible thing you can think of. And also, this is related to this paper of Anton, Henrique, and Eckhart, that, well, there's a little section that I rediscovered recently. I might have seen it before, but I forgot about it. Dirac cohomology. And I'm pretty sure this is related, but I couldn't find the precise relation yet. So in the calibrated case, and remember, well, you'll see in a second that sub-calibrations in particular induce calibrations of part of the structure. So in a calibrated manifold, both the guy that defines the foliation and the top power of the calibration, they are non-trivial in homology. And if you assume unimodularity, then all possible powers are non-trivial in homology too. What does that mean? I have no clue. Because again, but maybe this is, I thought of this as like nice because maybe it gives some insight on what the hell are Poisson homology computes. And yeah, it's connected to both this paper and also like there's this new paper on perfect Poisson manifolds by Davi and Eva Miranda. The proof is just absolute nonsense. This is just this guy is a volume form and everything follows from it. But let's go back to the triple splittings that we had here. I'm doing very bad with time now. So first, well, you had two distributions, I and K. So I is always a foliation just because it's gauge transformation of, well, this intersection, and both are involutive. Now, the star product of these two guys, which by first principles is Dirac, is just rescaling the I part of pi. So because pi itself, which didn't have this rescaling, was Poisson, this automatically implies that pi I and pi k are Poisson and commute. Also, the fact that pi I, the I part, is the product of omega and I, right? It says that this is pi I is calibrated by omega. Also, the fact that pi and k, well, one of those, we had these two. I should like perhaps not make so many comments if I want to reach the end. So it says that pi is coupling with respect to k, and omega is coupling with respect to I. So you have this. But now let's go to, so notice that up to here we had no concurrence. It's just the products being defined, right? But from here down, we can impose concurrence. So pi always splits as a Poisson pencil, but pi and omega, if you do circled star, you also rescale omega I. So because without rescaling it was closed, so these two guys concur exactly when omega I and omega k are closed. So that splitting of the form part is splitting into closed forms exactly when they concur. And also I mentioned that concurrence, you can switch signs, and then you see that this guy is just gauge transforming k by minus omega. So if this is Dirac, it means that k is a foliation. So concurrence also means that the splitting is in a foliation on both, yeah, transverse foliations. Now, let's go back to Lieberman. So if I and k are foliations, that is, if we're in the concurrence situation, and the foliations they define are simple, so given by S and T with connected fibers, then, well, let's see what, I'm doing terrible. So this and this were transverse, right? Graph of pi and k. So we know that their coproduct is a form. Also, this and this were transverse, so we know that their coproduct is a form. Now, this one is a form for no good reason. And this one that has no good reason to be a form, it's not. But they're all, yeah. So they imply that this very simple calculation implies that you find a diagram of 4 Dirac maps where these two guys, the T pushes both pi and omega to the same thing, which we knew because they were inverse to one another and graphs don't care about it. Okay, let me jump some stuff because we won't get there. Yeah, hierarchies. Okay, so, okay, if you have a Poisson structure and a closive form, we cook up this endomorphism, theta, and the following three things are equivalent. Pi 0 and omega 0 concur, or omega sharp is a homomorphism from the twisted bracket from vector fields into the Poisson bracket. So let me just say what this twisted is. So if you have theta, an endomorphism of Tm, I denote by uv with the theta on top. The thing, I forgot the name of this thing, but it's okay. So this is the twisted, the bracket, the Lie bracket twisted by theta, and theta is called Ninehouse when it's a homomorphism from this guy to the usual Lie bracket. Okay. Oh, sorry. And the third thing that these are equivalent to is that the form composed with the endomorphism is closed. Now, I learned very recently from finally having access to Magri Morosi, because I've been quoting it without having access to the paper. It was like some thing in Milano. But now there's a new paper of Yvette where there's a URL I clicked. And this condition, this third one, is what they called P omega structure. So a P omega structure is a Poisson structure in a closed-to form, such that when you cook up the endomorphism, the form part is closed. And then this implies two conditions from, again, things bifurcate into different directions. It implies, on the one hand, Pn structure, where, so n here is my theta, right? So it's a Poisson structure and a Ninehouse structure. And then automatically, like the Ninehouse with Poisson is again Poisson by general nonsense. And the omega n structure. So a closed-to form and a Ninehouse structure for which, and this is a condition, the composite is again closed. So that's kind of like what I was mentioning, that the Ninehouse condition, people got too hung up on it, and it's kind of like actually a consequence. It's more like, it's good to iterate. I don't even think that it's the most general thing to do recursion. But yeah, that's. So what were the hierarchies that, well, yeah, this is the classical hierarchy. It's already in that paper. Now I can say for sure, which is just, well, there they just took, they didn't put identity here, but I have a good reason for it. And it's equivalent if you take out the identity. So take powers of this endomorphism. They're all Poisson structures because this thing is Ninehouse. This guy is always, take powers, it's always closed. It's a little bit more complicated as this condition shows. And if they are, if pi 0 and omega 0 concur, then every possible guy you cook up there is they concur. Okay, so, but here I have to point out that the hierarchies that they construct, they, like, you start from pi 0 on the left, right, and omega 0 on the right, and then you go up with theta, and then you get pi 1, omega 2, and so forth. Yeah, well, let me, so I put the identity for, it will be clear in one slide more, like you can ask me in the questions just to get there to the end. Okay, so here's like already in that slide there's a hint. So if you, let's go back, like we're not in the form and by vector thing. Again, I'm arguing it's compatibility condition. Take a projection in the T plus D star, which has image L and kernel R, two Lagrangians. So it's written in this fashion. Like that's how it splits. So here var theta is pi and omega orthogonal, and the endomorphism you cooked, there's this very nice expression for it. It's theta identity minus theta. So who are pi and omega? Well, pi is their tangential difference. Omega is their cotangential difference. And theta is the unique endomorphism with the property that this guy is in L, and U minus this guy is in R. Okay, so if you have if you happen to be in the situation of this, this lemma, and pi 0 and minus omega 0, the minus is just like, I actually regret it. The evens should not have signs and the odds, yes, but that was a mess up. So if pi 0 and minus omega 0 are transverse and they concur, this should be concurring. I'm sorry, that was the old name. Then that forward hierarchy that I was describing here, it can be completed to a full hierarchy where you go down to. And you go down pretty much like, and that's kind of the reason for the identity plus, because identity plus this guy that goes, like there will be a guy that goes down, which is the var. And this, if you take its inverse, it's this guy. So the transversality condition ensures that this guy is invertible. And then with the other guy, I go down and I construct the negative things from this. And yeah, as you could expect, well, not only all of these guys concur, but as a consequence of this little thing here, which tells us what the eigenvalues of this recursion operator can be, you get a sequence. If you switch sign every 2 steps, or every step, then you get like a sequence of concurring splittings of everything. Yeah, and well, there are more concurring things that appear, but that was part of like that philosophy that, well, you really have to take the smoothness aside, and it's easier to talk about involutivity than, yeah, so for instance, if you switch signs from things, right, 2 guys concur if this guy and minus the other guy concur, but then I cannot guarantee that they are either by vector or form. The first step is Dirac always, because remember, like pi, where is it? Yeah, the graph of a bivector is cotangential to anything. The graph of a form is tangential to anything. So the first step is always defined, but the second one depends on what you cooked up in the first step. So, I mean, there's lots of things that concur and blah, blah, but I can't make sure that they are smooth. And I don't even know if I care. So, yeah, that was it.